Okay, morning. Okay, so then again, this week we have the quiz. Okay, so the quiz, the same format as before. So it's open book, open discussion, open everything basically. Okay, so make sure you go to your tutorial section, take the quiz, and get up 5%. Okay, so let's continue on using Laplace transform to solve differential equation. Okay, so this is a diagram I showed you in the previous lecture. Giving a differential equation, for example, y double prime, this second order. Okay. So instead of solving this differential equation in the pure time domain, we look at it from different perspective. We use Laplace transform and try to solve that by converting or transforming this differential equation into the S domain first. So basically the idea is, I showed you one example, is take Laplace transform both sides and obtain an expression for y of s. Okay? So the next step is to decompose this y of s into the simplest form or simplest item that you can get from the table that I gave it to you, basically this table here. Okay? So basically you break it down to this simple format here. Okay? And then use this table to find its inverse Laplace transform, which is y of t. Okay? So that's basically idea here. So we started basically, we're talking about how do we decompose this y of s. Okay, basically this portion here, how do we decompose this? Okay? And this portion here, just looking up the table. And we're going to look at different kind of cases. The first case I wrote it down, and we haven't got the chance of exercise yet. So when you have a simple pose, so the concept pose is basically your y of s, okay, is a numerator divided by denominator. The denominator, if the denominator is separated or breaking down into those simple format here, so this is what we call the simple pose. Okay, so those are real ones, P1, Pn, a real pose. So the next one we'll see not so simple. Basically, maybe there's s plus P1 to the power 2, so like a repeated pose there, right? So if you have this case here, then we decompose this y of s like this, okay, like this. And then all we need to know is what are the k1, k2, and kn. So I'm going to show you two different ways of finding k1, k2, kn. One way is sort of a simple way is here, using formula. Okay, so you look at this formula here. How do we find the k1 or ki? Is you do this basically. For example, you want to find k2, right? So then what you do is k2 will equal to s plus p2. Okay, so s plus p2. This is a pole associated with the k2. So s plus p2 multiplied by this guy. Okay, multiplied by this guy, original one. So you can imagine what happens if when you multiply with this original y of s. Then what happens is this s plus p2 will cancel out this s plus p2 here, right? Yeah. Then you set the s equal to negative p2, okay, to the resulted expression over here. So that's going to be the value of this k2. Okay, so let me show you an example here. Okay. So let's suppose I have a differential equation, and after this conversion, and I end up with my y of s, which is, let's say, s squared plus 12 over s plus 2, s plus 3, for example. So this is y of s. And apparently, this y of s is this case number 1, simple pose. So you separate that into, you don't necessarily have to use k1, k2. You can use any constant you want, okay, over s. plus k2 over s plus 2 and k3 over s plus 3. Okay. So the first one is s, so basically the pole associated with the s is 0, right? The second one is s plus 2, so the pole for this one is s equal to negative 2. So this is s equal to negative 3 for this pole here, right? Okay. So finding this k1, k2, k3, let's use the formula here, okay, to find the k1, k2, k3. So k1, okay, equal to s multiplied by y of s. So y of s is this guy here, okay, it's this. So s multiplied by s squared over 12, s plus 2, s plus 3. So apparently you see, you cancel this s at here, right? And end up with s squared plus 12, s plus 2, s plus 3. Okay. So I should write it down here, s equal to 0 for this one here, s equal to 0, and s equal to 0. Okay, yeah. So plugging s equal to 0 over this expression right here, so the numerator becomes 12 and denominator is 6. So 2. Okay, 2. So it's pretty straightforward. Is that good? So yeah, take a second look at this one here, see how it works. Okay, any questions? Now you got to be careful though. You don't plug in this s equal to 0 right away. Okay, so you plug in this s equal to 0 after this s got cancelled, because you know the reason you cancel this s, because if you don't cancel the s, you plug s equal to 0 here, you got infinite there, right? Yeah. Okay, so k2, same thing, will be s plus 2 multiplied by s y of s. Then you set s equal to negative 2. So s equal to negative 2. So that's the pole for this one here. And basically s plus 2 is cancelled. Okay, so we have this one here after the cancellation. So plugging s equal to negative 2 here, let's see what do we have. So s equal to negative 2, 2, 4, 4, 16. Negative 2, 1, so negative 2. So negative 8. Okay, similarly, okay, similarly. Similar to this step here. So s negative 3 into it, 9, 21, 21 over over 3, yeah, 7. Excellent. So that's k1, k2, k3. Then overall, your y of s, right? Instead of the numerator divided by denominator, you have this breaking down decomposed format, which is 2 over s plus, not plus anymore, 8 minus 8 over s plus 2 plus 7 over s plus 3. Okay? Yeah, so those are the simplest format that you can find from the table, right? Then we use the table to look for the inverse Laplace transform. Okay, so inverse Laplace transform, which is going to give us the y of t. Now this is 3, this is s, right? Now when you look at the table here, okay, make sure you can find the right one here. So let's say 1 over s, what would that be? So that would be actually this one here, right? Yeah. So that's either 1 or u of t. So then you can put this u of t here, but we put a 1 here because overall we're going to use everything multiplied by u of t basically. Okay, yeah. Second one is 8 over this, so that's 8 e to the power negative 2t, 7 e to the power negative 3t. So overall that's the answer here. Okay, yeah, yeah. Oh, this is 2. Sorry. Yes, exactly. Yeah. Thank you. Is that clear? Yeah. So this step here, I guess, it's a very simple formula. Okay. Just remember, how do you find the corresponding k? Use whatever that factor associated with that k, multiply with the original one, and set the resulted expression, okay, to the corresponding pole value. Okay. The other approach, okay, this is what let's call it using formula, right? This is using formula. So the other approach is more of a general approach. You can use the second approach to the other cases. Okay. So this approach is, let's call it comparing coefficient approach. So let's say you don't remember the formula now. Okay. If you don't remember formula, and there's no panic, and so we're going to try this approach here. Okay. So with our decomposed y of s still k over s, k1, k2 over s plus 2, and k3 over s plus 3. Okay. So this is the decomposed y of s. Okay. We're trying to find k1 to k3. Oh, by the way, you can always, okay, remember you can always double check. So basically combine these three terms together, see if you can get back to your original expression, right? That's how you verify whether you find the right k1 to k3. Okay. So comparing coefficients is, here's what we're going to decompose. So then what we do is, let's put this back to this original numerator over denominator. Okay? So put this back, it means what? Means k1 multiplied by s plus 2, s plus 3, plus k2, s by s plus 3, plus k3, okay, s multiplied by s plus 2, over this s plus 2, s plus 3, right? That's what I mean by putting it back. Okay. So you might think, what does it mean? Well, you see, this term divided by this term is k1 over s, right? And this term divided by this term is k2 over s plus 2. This is k3. So nothing changed. Okay, just putting it back here. Then for the numerator here, okay, technically speaking, it should be the same as this numerator. Okay, so that's what we mean by comparing coefficient now. So this numerator should be the same as this numerator. Okay, yeah. So now let's simplify this numerator here a little bit. So let's see what do we have. Okay, so for the top one and here, okay, so let's see how you basically we got k1, okay, s squared. Okay, so what I'm gonna do is this, I'm gonna group all the similar terms. So basically all the s squared terms, I'm gonna put them together. Okay. And all the s term, put them together. So I have 2, 5, k1s plus 6, k2s squared plus 3k2 plus k3s squared plus 2k3. Okay. Divided by s plus 2, s plus 3. Okay, so the numerator here, so I'll just write a numerator. Numerator here is s squared, k1 plus k2, right? So there, k plus, there's another one, k3. Okay, so that's numerator. 3 s squared terms. How many s terms? 1. Did I miss s term here? Oh, I missed s term here. This is s here, right? This is s here. This is s here. So how many s terms? 1, 2, 3. So s, 5k1, 3k2, 2k3. okay, plus one constant. No, this is k1, right? 6k1. Okay, plus one constant 6k1. Okay, so this is a numerator on the right side. So this numerator should be the same as the numerator of the original expression. So which means basically now what you see is comparing coefficients, okay, of a numerator. Then what's the other side of the numerator? The other side of the numerator is s squared plus 2. Okay, so we compare, basically meaning this k1 plus k2 plus k3 equal to 1. This 5k1 plus 3k2 plus 2k3 equal to 0. Yeah, 6k1 equal to 2. Okay, so to make it a little bit clearer, sometimes what you write is for s squared. Okay, for s squared, you have k1 plus k2 plus k3 equal to 1. For s coefficient, it's 5k1 plus 3k2 plus 2k3 equal to 0. And for the s to the power for the s to the, so this is s to the power 2, this is s to the power 1, so for the s to the power 0 term, which is basically the 1, you have 6k1 equal to 2. So you got three equations, three unknowns, and then you will have a unique solution that is here. Okay, yeah. So that's pretty easy to calculate. So that means k1 equal to 3. Sorry. 12. What's that? What's going on here? Oh, that's 12. 12. Okay. So k1 equal to 2. That's the same result as we find in the previous case, right? So k1 equal to 2 at here. Okay? Yeah. So sub the k1 equal to 2 back here, back over here, solve for k2 and k3. Okay? So you should get the same results, okay, as previously. So double check if this works. Okay? Any questions? Yeah. So this comparing coefficients, this is the general approach. Okay. For all three different cases, I'm going to give you it here. So even if you don't remember the formula or you don't know how to use the formula, okay, comparing coefficients. Yeah. But of course, the number one step is that you need to know that you are breaking down into the right or the simplest form. Okay. For the first case, when you have a simplest pose here, so those are simple pose. So you break or decompose like this. All right. Yeah. Okay. So now let's take a look at the second case. Any questions? Yeah. So second case is when denominator contains complex conjugate poles, or sometimes we call it roots. Yeah. So the denominator, so you look at the previous denominator, the solution for the previous denominator, basically when you set the ds equal to 0, all the answers are simple poles, right? It's like the three different cases we're dealing with when solving second order differential equation. The first case is when you have two distinct real roots, right? And the second case is when you have complex conjugate roots. And then the other case is when you have a double roots, right? Yeah. So this is basically the case like that when you have contains complex conjugate roots. So here is we'll look at it through an example here. Okay. So let's say, for example, we're gonna solve y prime double prime plus ay prime plus 25y equal to 20 e to the power negative 3t. Okay. So let's say this is what we're gonna solve, and initial condition is 0 and 0. Okay, to simplify the situation here. Okay, so if I want to solve this one using time domain, then I probably will use the undetermined coefficients. but I'm going to use Laplace here to solve. Then I'm going to have to take Laplace of both sides of this equation here, right? So taking Laplace, okay, then we end up with s squared capital Y of s plus, you're supposed to have those initial conditions get involved here, but in this case, initial condition is 0, so these two terms will be 0. And 8s y of s minus 8 y of 0. Okay, and plus 25 capital Y of s, okay, equal to the other side. This is 20 1 over s plus 3. Okay. So what I did is I actually just made use of properties of a Laplace transform for derivative functions. This second order derivative, so the Laplace transform the second order derivative, it's this. Laplace transform first order derivative is this, multiplied by the original 8. Okay. Yeah. Because initial condition is 0, so these two terms, okay, and this term is gone. Okay. Yeah. Then we group all the y of s term in here. So what do we have? We have y of s squared plus 8s plus 25. Okay, equal the other side, 21 over s plus 3. Okay, so that's the results after Laplace transform. Then, which means my y of s equal to 20 over s plus 3 s squared plus 8s divided by 25. Plus 25. Okay, so coming to this stage, okay, so this is the next step is decompose this y of s, right? Now you look at this bottom here, the denominator. So you have a simple pose here. Basically, the s plus 3 is the same. That's case number 1, right? That's case number. So basically, you will have a decomposed, let's say a over s plus 3 here. That's what we do, like a case number 1. So it's the question of the second one here. This s squared plus 8s plus 25. Now, technically speaking, when you have, let's say, ax squared plus bx plus c equal to 0, you can always break this down into two factors, right? Yeah. But the only problem here is you have to look at what is the solution for the x set here. So the solution for the x could be real numbers, could be complex numbers here. But for this particular case, this is like taking the characteristic equation. What's the characteristic equation? Is what? Lambda squared plus a lambda plus 25, right? Yeah, equal to 0. Okay. So you see this characteristic equation, that's the same thing as this s squared plus as plus 25. Okay? So when you set, so basically when you set this s squared plus as plus 25 equal to 0, set equal to 0, and solve for the s. Okay, you'll see that this s, okay, give you complex conjugate. Okay. Here, okay, you'll see that. So you can try it. So now, in this particular case, we're not going to basically break, because you have two complex roots. Then we're not going to break this x into minus complex, s plus complex, that kind of format there, right? Yeah. So then what we do is we're going to just retain this one as it is. Then you break this down just as it is. So bs plus c over s squared plus 8s plus 25. Now remember, this is what you do only when the denominator gives you this complex conjugate roots, right? Yeah. If you can break this denominator into two real numbers, two factors involving real roots, okay, then you do that. Okay. Yeah. So what that means actually, basically, giving a differential equation, and you transform everything into this one here now. So actually, the first step you do before you do the decompose is to check what kind of roots do you have for this quadratic term. Okay. If this one has two real roots, then you you basically have the first case, right? Basically the first case. But in this case, they have two complex roots, so we break it down into this. I'll explain why we can do this, okay? Yeah, but for time being, okay, just remember this is basically the rule here, okay? When you have two complex roots, break it down this, and then we can make use of these tables. But before we can use the table, we have to find ABC first, right? Yeah. So how do we find ABC? Finding A, you can do what? You can use this formula. So finding A, you can use the formula. Or you can try the comparing coefficients on all these A and B and C's. Okay? Yeah. So let's say, for example, if I use formula, okay, using formula, A will be S plus 3 by Y of S, and setting S equal to -3. Okay, so let's try this one here, and then we'll try the other approach, okay? So let's see, if I do this, what do I get? S plus 3 by original one here, so that S plus 3 is gone. So that's 20 over S squared plus 8S plus 25. S equal to -3. Okay, so plugging S equal to -3 into this denominator, so 9 minus 27 plus 25, so 9 minus 2, which is 7, right? So overall 20 over 7. Is that right? No. What I'm talking about here? No. So bottom here is 9 minus 24 plus 25. Actually 10, right? So 20 over 10, which is 2. Okay. So A is supposed to be 2. Okay, so then there comes B and C. So if I use the other approach, I'm going to use, okay, comparing. There's no formula to find B and C though, okay? Use comparing coefficients. So here's what we're going to do regarding how do we use comparing coefficients. So using comparing coefficients basically means you write this one back into this numerator divided by denominator. Okay? So which means my numerator here, okay, so let me rewrite this one here, that's A by S squared plus 8S plus 25 plus BS plus C S plus 3 over this S plus 3 S plus square 8S plus 25. Right, that's how you write it back. Okay, yeah. So the numerator here should be the same as the original numerator, but we need to clean it up a little bit first. Okay, so I'm going to write down at the bottom now. Then the numerator is this side of numerator is A. How many S squared? There are 2S squared terms. Okay, so A BS BS squared. That's A plus BS squared. How many S squared terms? There's 8A at here. Here you have 3BS plus CS, so that's 3B plus C. Right? How many constants? We have 25A, and then there is a 3C. Okay, that's basically, after cleanup, you should get this one here. Did I? No, so what's going on here? Yeah, I got it right. Okay, so this is the numerator after this decomposition here. And this numerator should be the same as the previous numerator. What is the previous numerator? 20, right? So that should be the same as 20. Okay. So 20 here basically it's this. It's a 0s squared plus 0s plus 20. Okay. So now comparing coefficients, meaning, okay, for s squared we have a plus b equal to 0. For s term we have 8a plus 3b plus c equal to 0. For the s to the power of 0 term, which is the constant term, we have 25a over 3c equal to 20. Okay, so 3 equations, 3 unknowns. Yes. Oh, yes. Thank you. Okay. So solving the 3, you should get A is 2, same as before, B is negative 2, and C is negative 10. Yeah. Good. So, which means I'm going to rewrite my y of s now. So that's 2 over s plus 3. B is negative, negative, so there are 2 negative things here. So minus 2s plus 10 over s squared plus 8s plus 25. Okay. So the 50% of the work is done. Actually, the next one is 60%. Then the next one is actually more important, is how do we find the inverse of this y of s? So here you need another little bit of skill at here, okay? A little bit of trick. Okay. Now, finding the inverse, the first one is easy because you have directly this 1 over s plus 3, 1 over s plus a in the table, right? But the second one here, okay, you look at the table, I guess we don't have anything that is even close to what we have here, right? So the closest to what we have is what? It's probably this guy and this guy. Because you see, for this one here, the denominator is a quadratic format. And you look at the table here, the only one that has a quadratic is either this or here, right? Yeah. I guess we're not going to use this one because there's no constant multiplied by s here. So this one here, when you expand it, this s plus a squared plus omega squared here. So that's basically what? S squared plus 2as plus a squared plus omega squared, right? So that's pretty close to what we have the numerator here. Okay. So then the next thing here is to do, okay, so if this is the one, then what all I'm going to do is I'm going to strive to trying to match what we have it here in order to use the table. Alright? So here's basically the trick that you're going to try to do this one here. So Laplace, so let me rewrite one of this one right here. Laplace of this one is s over a, okay, s plus a squared plus omega square. Okay. Yeah. So I'm trying to basically match with this one. Okay. Yeah. So this is what we're going to happen here. Now you look at this top right here. Maybe what I'm going to do, I'm going to do something to the bottom here. Okay. To match the bottom with this one. So here's what we're going to do. We can use so s squared plus 8s plus 25. So how do I transform this into this format? Well, you look at this one. This is s plus a to the power of 2, right? And then you end up with s plus 2as, s squared plus 2as plus 8 squared. Okay. Now you come back here. This is s squared plus 8s. Well, which means what? Which means my a at here gonna be 4, right? Gonna be 4 here. So this is basically s squared plus 2 by 4s. Okay, s plus 12, see that 2 by 4s match this 2as now. Okay, but you need to plus a squared. 8 squared is 4 squared here, so that's basically 4 squared. But you plus 4 squared, you had to what? Minus 4 squared. And then you have the original 25, so plus the 25 there. Okay, you see the transformation in here? So then, the first 3 term is s plus 2, and that's s plus 4 to the power 2. The last one here is 25 minus 16, which is 9, right? And 9 is 3 to the power 2. So now I have the denominator exactly the same as this one here. Okay? Yeah, so omega here is 3, and a there is 4. So that's how you do this with the denominator. Okay, so just a little exercise, you'll get used to this. Now let's try how to convert this numerator, okay, to match this. Not just this one here, okay? Remember we have also the other one that's e negative at sine omega t there, right? Okay? Yeah. So now what we do is with numerator here. So here's what happens, okay? So I'll just deal with this term here. So that 2s plus 10 over s squared. The bottom here I convert it to this now. I'm gonna try to write this one here. Okay. So yeah, concentrated here. Okay. Yeah. Yesterday I was sitting. Actually, I realized how difficult it is to listen to people talking now. Yesterday I was listening to people's presentation and I was almost falling to sleep. So really, it's very difficult actually to stay awake in the morning. But anyway, try the next step. Okay, we're gonna match this numerator with what we have it here. Okay, so how do I get the numerator here is s plus a here, right? S plus a. But I don't have s plus a here. I got 2s plus 10. So we're going to have here is, okay, I'm going to have s plus a. What's my a? A is 4, right? So s plus 4. Okay? So I'll just mandatorily, impose this thing in here. But I got a 2 here, so I guess I still need a 2 over here, right? I can't change things. Okay? Yeah. Okay, so now I got 2 bracket s plus 4. Now, this 2 bracket s plus 4 meaning I have a 2s plus 8, right? Yeah. So then I have to minus 8. Then plus 10. Okay. Over this s plus 4 square plus 3 square. Okay. So that gives me this 2s plus 4 plus 2 over s plus 4 square plus 3 square. So we're getting pretty close now. So then I'm going to separate this one. Okay, separate this one into 2 terms. One is this, okay, and the other is the other. Okay, so then I got 2s plus 4 over s plus 4 square plus 3 square. Okay, the other one is 2 over s plus 4 square over 3 square. Is that good? Yeah. So always remember, the purpose is to try to use the table here. Now, see if I can use the table now. Can I use the table for the first term now? Right? So you see this one here? That's exactly this format here, right? Exactly this format. Of course, there's a 2 at here, so all you need to do is just multiply 2 here. Okay? Yeah. The second one here. Okay, the second one here is that doesn't match this one here, but this is pretty close to which one now? Pretty close to this guy here. See, right? Yeah. So let me write this down here. So the other one is Laplace inverse, not the inverse. Laplace transform e omega t and then e omega e negative at sine omega t. Which is omega over s plus a square plus omega square. Okay. Yeah. So the second one here, we're trying to match this because the numerator here is constant. Okay, here's constant. And denominator, we already just matched the denominator. So the only mismatch is what? Is the numerator. So I guess I need to match this numerator with this omega. What's omega? Omega is a 3 at here, right? Okay, so then I'm gonna do is I'll just put a 3 at here. If I put a 3 here, I have to do what? Minus 3 here. Okay. So then overall, this 2, let's move this down 2 over here. Okay. So now you see this guy. That's exactly matching this one here. Okay. So all 2 terms and conveniently match the one in the table now. So then we can use the Laplace, inverse Laplace transform from the table. Okay? You see the trick? Yeah. So this is, yeah. Why don't I just use this red circle, and then what? Yeah? Okay. Yeah, take a second look at this approach here, okay? Yeah. First, you have to identify properly that you do have two complex roots. So then you don't decompose this anymore, just leave it as it is. And the numerator here is just bs plus c. Okay? So one order less than the denominator. Okay? Then you use comparing coefficient to find A, B, C values. Here. Now the next trick is to manipulate this term in here to match what's given in the Laplace transform table. And what we're trying to match is the inverse Laplace of this format and this one here. Okay? Yeah. First, to match this bottom, the denominator with this s plus a squared plus omega squared. Right? Second is to match this numerator with either this or this. So just for your exercise, you can come up with anything. Let's say maybe s squared plus 4s plus 2, right? So how do I convert this one into this guy here? Well, I guess the first step is you're gonna see if you have a complex roots or real roots set here when you set this one to 0, right? Yeah. And you're gonna get complex roots. So for this one here, if I match that, it's going to be s plus 2 squared plus, not really plus now. Actually, it's going to be, in this case, it's actually real roots, eh? It's actually real roots. No, that's plus 6 here. Okay, yeah. So if I have a 6 here, so that's s squared plus 4. Then there's a 2 at here. Okay, 2. Okay, so in this case here, a is 2. What's omega? Omega is root 2. That's right. Okay. In this example here, this one here, yeah, this is because this is 8s here, right? This is 8s. 8s is basically 2 by 4s. Because you see here, this is 2as. Okay. Yeah, 4 divided by 2. So here it's basically 4 divided by 2 is this a value here. Okay? Yeah. When do I what? What? Oh, well, yeah, because all we want, right? All we want is what? The objective is to solve for y of t, right? So what? But I'm not solving for y of t yet. I'm actually getting capital Y of the Laplace transform. So after we got the Laplace transform, then we take inverse. This is the next step. So inverse Laplace of this guy gave me y of t. That's what happens here, right? Yeah. Because y of t is the solution we're trying to obtain. So what is the inverse Laplace this guy here? It's the inverse Laplace. Put down everything in the bracket. It's a over s, so 2 over this s plus 3 minus which one? Minus let's see, where are they? Here. And minus this guy and this guy. Right? Yeah, that's the decomposition. So 2 s plus 4 s plus 4 squared plus 3 squared minus 2 over 3 and 3 over s plus 4 squared plus 3 squared. Right? That's the results of the decomposition at here. Okay, so then use the table. The first inverse Laplace 2e negative 3t. Second one here is 2e negative 4t cosine 3t. The other one is 2 over 3 e negative 4t sine 3t. Multiply by u of t. Okay, so that's the inverse Laplace transform. And that's y of t. That's the solution, right? So if you use a different approach, let's say for example in the time domain undetermined coefficients, you'll get exactly the same thing basically. Okay? Yeah. Is that clear? Yeah. That's okay. So you practice one or few examples, you'll feel much better. So the last case, okay, is when you have repeated roots, just like the 3 different cases, right? So here's the case here. So let's say y of s equal to 2 over s cubed s minus 1. So this is what I'm talking about, having repeated roots. Okay? Or maybe y of s is, let's say, maybe 2 over s minus 1 squared, right? So you see this one here is also repeated, this is repeated, s equal to 1 is repeated twice. Over here, what is repeated twice? 3 times. S equal to 0, repeated 3 times. Okay? Now you see here, this s equal to 0, okay, is a repeated pose. And this s equal to 1, okay, it's a repeated one. Okay. So what do? Here's what you need to follow here, okay? So for the first one, we're going to decompose this one into this format here. 2 over s squared. No, sorry, not 2. We don't know yet. So a over s, b over s squared, c over s cubed, plus d over s minus 1. Okay, so that's what this one here. And second one here is going to be a over s plus b over s minus 1 plus c over s minus 1 squared. Okay? Yeah. Then how do I find ABCD or ABC? Comparing coefficients. Okay, so again comparing coefficients. Sorry? Yeah, for the A here you can use a formula. For the B, actually for C here, now yeah, you do have a formula, but I'll let you know what the formula is. The formula is more of a general formula here, right? I'll give you the formula, but just in case you don't use the formula right, you'll get a wrong answer, right? But the comparing coefficients is actually more straightforward, yeah. So in my lecture notes, I do have a formula for this kind of case. But I would encourage you to use comparing coefficients. The reason is I might not give you a very sophisticated, s to the power of 4 or 5, right? That's too big. Maybe just s to the power of 2. Repeat it twice, right? Yeah. So it won't be that bad. Any questions? All good?